All right, today we're going to talk about a really fascinating and frankly pretty dangerous type of software bug. Now, I'm not talking about the kind of bug that makes your app crash or just act glitchy. No, we're talking about something way sneakier, a hidden flaw where the code works perfectly, but the results are an absolute disaster. These are the ghosts in the machine.
So let me just start with a question for you. What's a bug that isn't a bug? It kind of sounds like a riddle, right? But it's actually the key to understanding one of the most subtle and damaging threats in cybersecurity today, something we call a logic flaw.
So, what are we really getting at here? Well, we're looking at flaws that aren't about the quality of the code, but about its fundamental thinking. It's that moment when an application follows every single one of its instructions to the letter, but those instructions are marching it and all of your data right off a cliff.
And here is the perfect way to picture the difference. A traditional bug, like a missing security patch, that's like having a broken lock on your front door. It's an obvious weakness. But a logic flaw, that's a perfectly built, high-security door. It works flawlessly, except it was designed to lead you straight into the bank vault instead of the hallway. The door itself is perfect, but the logic behind where it goes is catastrophic.
Okay, so let's put a more formal definition on this. An application logic flaw is a vulnerability that comes from a mistake in the app's core plan, its business logic or its workflow. This isn't about typos in the code or syntax errors. The application is doing exactly what it was told to do. The problem is, what it was told to do was based on a flawed assumption. The rules themselves are just wrong.
To really get the impact of this, let's look at a real-world cautionary tale. Our first case study shows how something that seems totally helpful can turn into an absolute security nightmare. We'll call this one the leaky error message.
So picture this. There's a new financial services app on the market. And like any new piece of software, it's got some bugs. So to help their support team track down these problems, the developers decided to create these super detailed, really verbose error messages. On the surface, that sounds like a smart, practical decision, right?
And this is where the flawed thinking comes in. This is the whole ballgame. The developers, they assumed this was totally safe. Their logic was, hey, all this data in the error message, the user can already see it in their own browser session, so there's no new risk. But an attacker? They ask a totally different question. They think, that's great for one user, but what if I can get the error data for everyone?
And because of that one flawed assumption, the floodgates opened. This wasn't just harmless debug info. Attackers could literally harvest usernames for password guessing, they could steal session tokens to hijack accounts completely, and they could even see the URLs people were trying to access. And get this, they could even capture sensitive stuff like passwords that users were typing right into a form.
Now, here's the kicker. The attack was ridiculously simple. First, an attacker finds the one single URL that displays the latest error for the whole system. Then they write a tiny script to just ask for that URL over and over and over again. We call that polling. And then they just sit back and log the results. Every single time another user, anywhere in the world, hit a bug, their sensitive data popped up on that page, and the attacker just scooped it all up.
All right, let's move on to our second case study, which is, believe it or not, even more subtle. At first, this just looked like a completely random, bizarre glitch that was driving customers absolutely nuts. This is the story of racing against the login. Just try to imagine this for a second. You go to log in to your banking app, but instead of seeing your balance, you're looking at someone else's account. You can see their transactions, their personal details, maybe even move their money. This was the crazy reality for customers of a major application. And it didn't happen every time, just sometimes, which made it almost impossible to diagnose.
The root cause here was a classic logic flaw called a race condition. It's basically what happens when the security of a system depends on the perfect timing of different events. For just a tiny, critical window, we are talking milliseconds here, the system is vulnerable. And an attacker, or in this case, even just a couple of unlucky users, can race to hit that tiny window of opportunity.
This timeline really shows you how that ghost gets into the machine. So at time 0, user A starts to log in. The app writes their ID to some temporary spot in memory. But bam, just 5 milliseconds later, user B logs in. Because the app was using a shared, static spot for that data, it overwrites user A's ID with user B's ID. A few milliseconds later, when the system finishes user A's login process, it goes back to read that temporary spot, and it pulls user B's ID by mistake. The result? User A is now logged in as user B. Insane!
Okay, so these flaws are subtle, they're sneaky, and they're incredibly dangerous. But, and this is the good news, they are absolutely preventable. This isn't about some kind of magic fix, it's about disciplined engineering and having a security-first mindset. So let's talk about the developer's shield.
So if we look back at our 2 case studies, the root cause was basically the same thing, using a shared, public place to store data that should have been private. The fix is actually pretty simple in concept. For those leaky error messages, the data should have been kept in a private, session-based container for that one user. For the login race, the user ID should have been handled in its own private space, separate from everyone else. The lesson is simple. Never, ever mix one user's data with another's, not even for a millisecond.
But beyond just those specific technical fixes, preventing this stuff really starts with a solid foundation. That means writing down every single assumption you make when designing a system. Why did we build it this way? What do we think will happen? It means commenting your code so the next person understands the intent. And maybe most importantly, it means you have to think laterally. You have to think like a hacker when you're reviewing code and challenge every single one of those assumptions.
So here's the big takeaway. You have to treat all incoming data as if it's potentially hostile. Never, ever trust user input. Every decision about who a user is and what they're allowed to see, that has to come from secure, server-side session data, not from some temporary variable that can be messed with. You have to validate everything, because that one time you don't, an attacker will find that opening.
And all of this brings us to what I think is the final and most important takeaway of all. Preventing these ghosts in the machine isn't just about following a checklist of rules. It really requires a fundamental shift in how you think.
At the end of the day, you can't just code your way out of this problem. You have to think your way out of it. It takes a creative, almost adversarial mindset where you're constantly asking, how could someone misuse this? What did the original developer assume would happen here? And how can I break that assumption?
And this quote from the source material just says it all perfectly. The most important challenge when probing for logic flaws is to try to get inside the developers' minds. You have to understand their goals, the deadlines they were under, the shortcuts they might have been tempted to take. Security, in this sense, becomes a game of psychology.
So I'll leave you with this question to think about. The next time you log into an app or you see some weird error message pop up, just ask yourself, what are the hidden rules here? What flawed assumptions might be running right now on your phone or your computer? The ghosts are a lot quieter than you think.